Computer Science 461, Evaluating System Performance. An overview of techniques and an introduction to operational analysis. A lot of the information in this presentation is from Raj Jain, who wrote the book on the subject literally. His Art of Computer Systems Performance Analysis is the hallmark of this area of study, and I highly recommend it, as well as JP Buzen's original article on operational analysis. And just to motivate this can actually be a real-world problem, and there was an article in 2014 Wired in September about Twitter being broken almost every New Year's Eve when it turns midnight in Japan due to the number of people tweeting out Happy New Year wishes from Japan, because there tends to be a synchronization there that's not experienced elsewhere around the world. So the amount of traffic actually took down Twitter. I believe it was in 2012. It actually broke Twitter completely, and how they used techniques from this area of software engineering to actually make their system more resilient to these midnight tweets. So there are three general techniques for evaluating system performance analysis. One is analytical modeling, two is simulation, and three is measurements. Now there are some trade-offs from these techniques that we'll see on the next slides, and usually it's between accuracy and the amount of time that's required to actually pull it off. So let's take a look at these trade-offs between the three different techniques. So on the left you see analytical modeling. This is pretty much similar to code inspections in that you can do it at any stage of the software engineering process. A small amount of time required to do this. This is why we're discussing it. The tools that you need are an analyst and usually a piece of paper and pencil, or it can be done with a tool like Excel. It doesn't have the best accuracy, but it is easy to do and it's low cost. And I guess another drawback to it is the scalability is low. It works for small systems, but as the system gets more complex, it doesn't work as well. Simulation is good because you can build a simulation of the system. It can take a varying amount of time to build a simulation. In some cases it's taken longer to build the simulation than it has to build the actual working system. Tools that you work with to build a simulation are programming languages and platforms. You get pretty good accuracy out of it, and it's moderate in terms of its difficulty. Cost is moderate, and scalability is, it can scale up, but it doesn't scale up as easily as some of the other techniques such as measurement. And the last technique, of course, is measurement. Here you need a working system, so that's the real trade-off. That's the real drawback to this. Once you have the working system, you can actually instrument it, and the time to do that is varied. You do need some form of instrumentation or putting in appropriate breakpoints or time points that you're writing out to log files, or a system that automatically does that for you, like Segway's Silk Performer. The accuracy, it's variable. Usually this is the most accurate, and now Jain actually listed as difficult, but with some of the new modern tools it's certainly less difficult, although the modern tools do cost quite a bit of money, but you do get scalability in return for that. So we'll be discussing analytical modeling and measurement. We'll leave simulation for another discussion. So 3 rules of validation. 1, until validated, all evaluation results are suspect. So in general, don't trust the results of any one approach until it's been validated by one of the other 2 approaches. And don't rely on one technique too much. Your results should not be counterintuitive. So in order to get a measurement on system performance, you need to determine what it is you're going to measure. And you'll need to select metrics for 3 different outcomes. One is for successful service, so what do you want to measure when the system is actually successful? What do you want to measure when there's an error condition? And what do you want to measure when the system is unavailable? You select metrics for each of these outcomes, and keep in mind the mean value is important. That is, the average value is important, but so are other things such as variance and standard deviation. So how far do things vary from the mean? If you have high variance, the mean doesn't give as good an indication of performance. You also need to select individual or global metrics. Individual metrics reflect the utility of each user, while the global metrics reflect the system-wide utility. So individual metrics are things like response time or throughput for individual users, whereas global metrics are the utilization. That is, how busy is the system, how much is it utilized, its reliability, availability, overall response time, and throughput. In general, try to make sets of metrics as complete as possible. You can always add new ones. For example, the probability of disconnection. So, commonly used ones, one is response time, and the response time is typically defined as the time between the user's request and the system's response. Now, we'll see on the next slide you need to define this pretty carefully so it's not ambiguous, because there can be some ambiguity in terms of response time and what it actually means. Reaction time is the time between the submission of the request and the beginning of the processing. It's harder to get reaction time in my experience, and you have to be careful in defining response time. So here's a timeline of how a request would go through the system. You would begin with the user starting the request and then finishing it. Then the system starts its execution, does its processing, starts the response, completes the response, and then the user starts another request. So you can see the reaction time is between the user finishing the request and the system starting execution. The response time definition 1 is when the user finishes the request to when the system starts the response. And the response time definition 2 is when they finish the request to when the system completes the response. So again, you have to be careful in terms of indicating exactly what you are defining with response time. And think time, of course, is after the system completes its response and the user starts another request. So some more commonly used performance metrics. One is stretch factor, and that's the ratio of the response time at a particular load compared with the response time at a minimum load. The response time of the system generally increases as the load on the system increases, so you will get a stretch factor in there. The throughput is the rate at which requests can be serviced by the system. That is the number of requests per unit of time. For example, we can handle 50 requests per second. Now, often the throughput is the inverse of response time, but this is not always the case depending on your definition of response time and the system load. And another thing you want to look at is something called knee capacity, and this is the point at which the system begins to slow down in terms of response time and its throughput. And you will have both a knee capacity for throughput and one for response time. So with the throughput, you'll see there's a point here where the knee is located where it's not going to get any more throughput, and in fact you can see the throughput decreasing. The response time, likewise, you also have a knee here where it begins to build upward. So at first the response time is constant, and then it will begin to build upward, and that's the knee capacity for response time. So you always want to be cognizant of what your knee capacity is on your system, the point at which it begins to slow down. More commonly used performance metrics, one is efficiency. That's the ratio of usable capacity to the nominal capacity. Utilization is a fraction of time and resources busy servicing requests, and idle time is the complement of utilization. Utilization, efficiency, and idle time can also be useful as business metrics. If you have a low utilization, that may not be good because the system may not fit any particular business need or people aren't using it. So that's one that's a nominal is best metric. You kind of want that one in the middle. You don't want it so high that the system is busy 24/7, but you don't want it so low that nobody's actually using the system. Reliability, that's the probability of an error or the mean time between errors. Availability, the fraction of time and resources available to service requests. Generally, you want that around 99.9% or somewhere in that area. And you can also measure availability by the mean time between errors. So, utility classification for performance metrics, I talked about this just a little bit, but some metrics higher is better. In other words, users prefer higher values. You'd like to have higher throughput. lower is better, the users would prefer lower values. You prefer response times that are lower. In fact, you would prefer a response time that's less than 1 second compared to one that's 3 seconds. Nominal is best. You want neither high nor low values. For example, utilization, as we discussed a couple slides back. So when you're setting your performance requirements, you want, for your metrics, you want SMART metrics. And this is how Jain defines them. You want specific, measurable, acceptable, realizable, and thorough selection of metrics. So for doing this for continuous quantities such as response time, you basically complete a experimental design. Usually full factorial is what you want, although you can have a fractional factorial, and you may want to take a look at Hicks or Jain for how to do an experimental design. Basically, you determine your experimental factors and levels. So here's an example. We'd have one of two systems and 3 levels of users, low, medium, and high. And we want to measure response time. In that case, we'd have to run 6 different experiments for a full factorial design, and we could run as many replications as we saw fit in order to get a good bound on the statistics we were getting. And we would conduct a statistical analysis. We'd get the average, the mean, median, and mode for response time, standard deviation, which would indicate as a measure of variance as well as variance itself. So, if those were high in terms of standard deviation and variance, then we'd want to lower those numbers down so that there was more consistent experience with the users. Confidence intervals, those can tell basically 90, 95, or 99% of the time where a number is going to lie. And then conduct an analysis of variance to see which factor plays the largest role in terms of the response time or the outcome variable that we're looking at. If you're interested in this, there's also techniques for non-parametric statistics, but that's beyond the scope of this class, and for that you would look at statistics for social sciences. So that covers a basic overview of instrumentation in order to determine performance. And now let's take a look at analytical modeling. Now this is a very quick overview of operational analysis and for analytic modeling. So analytic modeling, there are 2 types. One is queuing models, for example MM1 queues or GG1 queues. And for these queuing models, the first letter indicates the distribution of arrival time, the second is the distribution of service time, and the third is the number of processors or services available. And operational analysis, which is also called mean value analysis, which is a little bit easier. So let's begin by taking a look at this operational analysis. It was developed by Jeffrey Buzen in 1976 and later extended by Peter Denning in 1978. That's Peter Denning, not W. Edwards Deming, who we'll talk about a little later in the class with his techniques of total quality management, but they are different people. The cool thing about operational analysis is it doesn't require any assumptions about distribution of service times or the inner arrival times. However, you do need some assumptions, and all these operational definitions are based on the assumptions that the measurements are collected during the observation interval. The per job and per service completion averages are computed at the end of the interval using simple division. You don't use any more advanced techniques than that. You assume that the time units for the length of observation period are also used for other time-dependent qualities. So keep those time units consistent. Processor and devices in the system must be numbered so that each refers to a unique entity. So don't confound the things that you're measuring. There are a fixed number of interactive terminals, and each terminal has an interactive process associated with it. And this is necessary for the response time law to hold. If the number of interactions during the observation interval is large in relation to the number of interactive terminals, then we can apply a simplification of the response time law. So these are the quantities that we can measure over the finite observation period. We're interested in number of arrivals, number of completions, and the amount of time the system is busy. So we can measure all three of those things, and then from there we can derive several operational quantities. One is the arrival rate, lambda sub I, which is the number of arrivals divided by time. Xi sub I, which is the number of completions divided by time, and that gives us our throughput. Utilization is the busy time divided by total time, and the mean service time is the busy time divided by the number served. So you can see these are pretty easy to calculate algebraically. The utilization law says given the number of completions C sub I and the busy time B sub I during an observation period T, then utilization is equal to the service time times the throughput. The forced flow law says for a given device I, V sub I is the number, these are the visits, number of requests made to that device, C sub I divided by C0. Due to the balanced flow job assumption, A is equal to C plus some small epsilon. And the throughput is equal to the throughput times the number of requests made to that device. Little's law says if R sub I is the response time per visit to the ith device and Q sub I is the number of jobs in the ith device, then Q sub I is equal to X sub I times R sub I. So the interactive response time law says the system throughput is equal to X is equal to the total number of requests divided by time. N is the number of jobs in the system, and Z is the user think time. Then R is equal to N divided by X plus Z. The service demand per device can be calculated if the service time for the ith device is Si and V sub I is the number of visits to that device, then D sub I is the total service demand per job of the ith device, and that's equal to S sub I times V sub I. And given that these are all algebraic quantities, again, they're pretty easy for you to compute. You just have to keep track of which one is which and not confound different things. Keep your time units consistent and number each device, and don't mix up visits from one device to another. Now let's look at queuing theory. It's still going to be algebraic in nature, but a little bit more difficult algebraic manipulation. And you also have to make some decisions with queuing theory. So let's take a look at modeling with queues. You can basically use mathematical equations to model the behavior of queues. And the type of model you choose for the queue depends on how the processes or customers arrive and how the system provides service to them. Now the simplest type of queue to model is the MM1, where there's one queue and both arrival times and service times are exponentially distributed. Here M stands for Markovian. So in order to model such a queue, you only need to know the arrival rate lambda and the service rate mu. From these you can calculate rho, or the traffic intensity. That's the arrival rate divided by the service rate will give you the intensity of the traffic. Now, if you have more service capacity than you have arrivals, the system is stable. If you have more people arriving or more jobs arriving than the system can serve, then the system becomes unstable. You can calculate the mean response time as 1 divided by mu divided by 1 minus rho, and you can calculate its variance as 1 divided by mu squared divided by 1 minus rho squared. So that'll give you both the expected response time and its variance. And again, MM1s are the simplest type of queues. They can get far more complicated than this. Other calculations, you can determine the probability of n jobs in the system, and that's P sub n is equal to 1 minus rho times rho raised to the n. Mean number of jobs in the system is rho divided by 1 minus rho. Variance is equal to rho divided by 1 minus rho squared. Mean number of jobs in the queue, so these are jobs that are waiting to be processed, is rho squared divided by 1 minus rho, and the variance of the number of jobs in the queue is rho squared times 1 plus rho minus rho squared divided by 1 minus rho. You can also calculate mean waiting time and the variance on the waiting time. Utilization is divided by the inter-arrival time divided by the service time. And there are quite a few other calculations you can make. Take a look at Jain to see all the different calculations that can be derived. So Here's an example. Assume you have 125 jobs that are arriving per second, and you have the capacity to process 500 per second. Here the utilization is equal to 125 divided by 500, which is 0.25. Again, that's a good utilization. We're using about 25% of the system capacity. You want a nominal as best. You don't want that to be 0, and you don't want it to be 1. Mean number of jobs in the system, if you run through those calculations, you'll get 0.33. And the mean time in the system is about 2.66. There are other types of queues. MM1B is an MM1 queue with some buffer to hold excess requests. MMM basically will have M queues instead of a single queue. G's are general arrival and service times, which you can't make as many calculations with, but they're pretty good. And that'll wrap it up. Next time we're going to have some brief words on security assurance from Somerville, so make sure to take a look at that chapter.